For today's notes, we're going to be going over section 5.5, which is dividing polynomials, which involves the remainder and factor theorems. Your essential question is, how can I divide polynomials? The first method to divide polynomials is called polynomial long division. So there's two methods that we're going to go through today, actually really just one. Polynomial long division is the much more tedious, much more difficult method to divide polynomials, so I will not require you to do this. If you would like to look at how to divide polynomials using long division, I have a video posted in the 5.5 folder in Schoology explaining it. For everyone else, you can just skip these first two problems, or really you can skip the entire front page, and we're going to move on to the next part. So the best way to divide polynomials is using something called synthetic division. Synthetic division uses synthetic substitution to help us take one big polynomial, which we call the dividend, and dividing it by some smaller polynomial, which is called the divisor. So to start, we're just going to go through the division process, and then we're going to talk about how that division process helps us factor polynomials that we wouldn't know how to factor otherwise. So I'm going to start by taking my divisor, x plus 5, and setting it equal to 0, and solving. So that would give me -5. I subtract both sides by 5. That's going to become my box number in synthetic division. So what we need to do now is we need to look at the dividend, and we need to figure out how many coefficients we need to set up for our synthetic process. So looking at my first number, it looks like I have an x to the 4th, so I need to lay out an x to the 4th coefficient, x to the 3rd, 2nd, 1st, and constant. So the number that goes with x to the 4th is the number that's attached to that x to the 4th term. So I see, even though there's no number there, I know that that's a 1. So 1x to the 4th, followed by a 4x to the 3rd. We're getting that from here. Then a 16x to the 2nd, getting that from here. Oh, excuse me, that's not right. So what comes next is x to the 2nd. I don't have an x to the 2nd term over here. It's being skipped. So what you need to do, if there's no term for that exponent of that x, you write a 0. Then I have a 16x to the 1st. And finally I have a constant, which is a number with no variable attached. That would be -35. Once we have all our coefficients, I can draw my line in, leaving a little space between my numbers in that line, and then I do my synthetic process. So I drop the first number below the line, and then any number that's below the line, I multiply it by the box number, which is -5. That's how I move diagonally. So 1 times -5 is -5. Now, once a number is above the line, I will add it by the number above it. So I'm going to take 4 and I'm going to add it to -5. 4 plus -5 is -1. Once you have a number back below the line, you start over. So -1 times -5, we're multiplying now, gives me +5. Now that I'm back above that horizontal line, I take 0 plus 5. And then -5 times 5. Then 16 plus -25, which is the same thing as 16 minus 25. I believe that's -9. And then -5 times -9 is +45. And -35 plus 45 is +10. The last number in synthetic division, this is your remainder. So what we're going to do now is we're going to take all these coefficients, so this number, this number, this number, this number, and we're going to use these 4 numbers to build a new polynomial. We're going to build the answer to our division problem called the quotient. The way I build it is I'm going to assign x's to each one of those highlighted numbers. The question is, how many exponents should I put on each x? The way you figure that out is you look at your original degree. So my original degree was 4 in the dividend. However many times you do synthetic division is how many you take away from the original degree. So my starting degree was x to the 4th, 4. I did synthetic division once, so 4 minus 1 is 3. So my new degree, my new highest exponent term in my x is now x to the 3rd. So I took that number and I made that the coefficient for x to the 3rd. Once you have the first term set, you just count down in perfect order from there. So it would go x to the 3rd, x squared, x to the 1st, and then constant. So my next term will have a negative 1, and then it will get an x to the 2nd, followed by positive 5. It gets x to the 1st, and then my minus 9 is a constant. What we do for the remainder is the remainder becomes a fraction. You write remainders like this. You put the number that you get on top, and you put the divisor on the bottom. So this fraction would look like 10 over x plus 5. Remember, we get that divisor from the smaller polynomial in our division problem. So this remainder, we're going to add it on as a fraction. 10 will go on top, x plus 5 will go on the bottom. That is going to be our quotient. For the next two parts of notes, you can go ahead and pause the video and get these definitions copied down. The remainder theorem states, if we divide a polynomial by some divisor, the remainder is obtained by finding f of a. So really, in plain English, all this means is if I take some dividend and divide it by some divisor, the remainder will be my last number of my synthetic division. Factor theorem states, well, what if this last number at the end is 0? If that's the case, then your box number is actually a solution to that dividend. So we're going to do a couple examples when we have a remainder of 0. Here's one right here. So notice how the directions have changed now. No longer is it telling us to divide, it's telling us to factor this polynomial. Now, I know some of you might be looking at this and saying, well, this polynomial has 4 terms. I know how to factor something with 4 terms. I can factor it by grouping. Well, let's go ahead and try that right now and see if we can factor this by grouping. So remember, we group these up into 2 groups. In the first group, I'm looking to pull out a GCF. So I can take out an x squared, leaving me with 3x minus 4. And then in the second group, I can take out a GCF. I think the only number that goes into 28 and 16 is 4, so I could pull out a negative 4, since the leading term is negative. And then that's going to leave me with positive 7x plus 4. Now the reason why we'd have to stop here and say factor by grouping does not work is because, look, now we have 3x minus 4 and 7x plus 4 as these leftovers. These should be the same. If they're not the same, then you cannot factor by grouping. So what we're going to do instead is we're going to turn this dividend, this big polynomial, and this smaller polynomial that we were told is a factor, we're going to turn this into a division problem. So it's going to look like this. 3x to the 3rd minus 4x squared minus 28x minus 16 divided by x plus 2. So the whole goal of this problem is to take this polynomial that is unfactorable given our current knowledge of factoring and turning it into something that we can manage with the factoring methods that we've learned so far in class. So anytime I start one of these problems, before I start doing synthetic division, what I want to do is I want to make a list of all of my answers, and I want to write what they should look like. In this case, we're being told to factor. Remember, factors are sets of parentheses. Something to keep in mind with these division problems is the degree of the big polynomial will tell you how many factors or solutions that you should have. So my highest exponent, my degree is 3, which means I should have 3 factors, or 3 sets of parentheses. What we've been given is already one factor. We've been given x plus 2. We're setting that as our divisor, and that's going to allow us to do some synthetic division to turn this big polynomial into something that we can factor. So here we go. As we learned from the previous example, I'm going to take my divisor, I'm going to set it equal to 0, I'm going to solve for x. That's going to be my box number for synthetic division. Now I can look at my dividend, this piece, and I can set this up in my synthetic coefficients. So we need x to the third, x squared, x to the first, constant. So that would be 3x to the third, negative 4x squared, negative 28x to the first, negative 16. Make my line, drop the first number, multiply by the box number, and then add, multiply by the box number, and then add, multiply the box number, and then add. Notice how our remainder is 0. That's a good thing. If you get a remainder of 0, that means that you have created a polynomial that we can potentially do more math with. We can factor it further. So I need to take this 3, this negative 10, and this negative 8 and turn it into a new polynomial. We apply the same logic from our previous synthetic example. So I know that if I start with a degree of 3, I do synthetic once, our new degree is going to be 3 minus 1, or 2. So this is now not 3x to the third, this is now 3x squared, which makes this minus 10x to the first, and the minus 8 my constant. So this is our quotient to this division problem. I can now take this quotient, since it only has 3 terms, and I can actually try to factor this now. Remember, if you see 3 terms in a polynomial, you can factor it by the AC method. My a times c is negative 24. My b is negative 10. Is there 2 numbers that multiply to negative 24 and negative 10? Why don't you pause the video and see if you can find it on your own before I reveal the answer. So, if you've tried this on your own, you should have gotten negative 12, positive 2 to complete this AC method factoring scenario. Because my a coefficient is not 1, I have to rewrite my middle term, minus 10x, as minus 12x plus 2x. And now this is going to be a factor by grouping problem that's going to work. First group, greatest common factor is 3x, leaving me with x minus 4. Second group, 2x minus 8, greatest common factor is positive 2, leaving me with x minus 4. Hey, now these leftovers match. That's a good thing. That means we're doing it right. So I can take the GCFs, the 3x and the 2. That becomes one factor. And then those matching leftovers is the other factor. And that is going to be the other 2 pieces of my answer. So because we were able to do synthetic division with this big dividend polynomial, we were able to turn it into something that is more manageable for us, something that we can do AC method with, and that allowed us to find all 3 of our factors. Another type of problem you might see is one that says not to completely factor, but to find zeros. So what we've been given here is we've been given 1, 0. A 0 is the same thing as a solution, which is the same thing as an x-intercept. They all mean the same thing. They're all synonyms of each other. Whatever the degree is of a polynomial, it will tell you how many zeros or solutions that you should get. Our degree is 3, so I should get 3 numbers as my solution. What we're going to do in this problem is the exact same thing we're doing in this problem, except we're going to have to go one step further. You will see in just a second. So I have been given one number that if I plugged it in to this function, it would create a result of 0. It would be 3. So that is one of our solutions. That is what the factor theorem is. So now I know one of my box numbers for synthetic division. It's 3. And then I can set up synthetic division with this big polynomial f of x. Where it's 2x to the third, negative 11x squared, positive 3x to the first, and then a constant of 36. And I can do my synthetic process with a box number of 3.